Okay, plan today is 10.3, the Fourier convergence theorem. So let's write out what that says. So this is an if. We have f and f prime are piecewise L L F prime outside of the same interval. So it is periodic with equaling to L. Then our function will be defined or be equivalent to a naught over 2 plus 1 to infinity is then sine n pi L plus then sine n pi x over L, where our a sub n is going to be equal to 1 over L integral negative L to L x n pi x over L x and equaling 0, 1, 2, and so on. Let me clean this up to make some of these letters look like what they're supposed to look like. S, that's N, and that's an X. Our B sub N, 1 over L, integral negative L to L, X, sine N, L, X for N, 1, 2, 3, and so on. But wait, there's more. Yeah, the Fourier series. Converges fx for x such that f is and to half x plus, so limit as x comes from the right plus f of x minus, so as x comes from the left, x such that is let's see how that looks. Close enough. Slight spacing issue with my converges too. So a couple of things to draw attention to. We have our normal equation that we did before for Fourier series, and our normal A's and B's, noting that we start A at 0 because we have it out front, but B we start at 1 because that's what our summation is. Now, what's this stuff on the bottom mean? So, for example, if we had a graph that looked like this. When we do the Fourier series, it's not going to distinguish between a point being up here or down here, or up here or down here, where it's defined on the actual function. And where's the open point, where's the closed point? It's just going to put a point right there in the middle. So it's going to average the two y values, or the two limits, whenever there's discontinuity. And actually, you can think of it as averaging them all the time, but in spots where it's continuous, like along here, it's just going to take the value, and it's going to be able to just work perfectly. But discontinuities give us problems. So we're going to have that spot in the middle that gets averaged on. So let's do another full example of this. Zero for L, we get negative L, 0, and then we go 0, L, and then f of x plus 2L equals f of x. Well, so let's label our graph. Now it's an open circle there, coming over, closed circle. That's supposed to be on the actual axis. Open circle, over, closed, open, closed, open, closed, closed, and we go from there. So that's what it should look like. Whenever we do the Fourier series, though, I'm just going to put spots here for all our discontinuities. And these will all be open circles, no matter what's happening at them. Some of them are already open circles, so that's fine. But the ones that are filled, they become open circles, and we're going to put the points right there. So what is the Fourier series actually going to give with the formula? You get something that's actually called the Gibbs phenomenon, which there we go. In reality, what's going to happen is it's going to have bad oscillation here. Oops. Bad oscillation. And it's going to settle down and be about the same. Then bad oscillation, jump. Bad oscillation, over. Bad oscillation, jump. Bad oscillation, over. Jump. So whenever we have discontinuities, have a bad oscillation on either side of that discontinuity. So I'm going to redraw this. I'm going to just delete that blue. If I can delete just the blue. And I'll redraw it over here. And red's a good color. So big oscillation, jump, big oscillation there, big oscillation, jump, big oscillation. So it's kind of like whenever it makes a jump, it has to build up momentum to make that big leap. So it starts vibrating to make the jump. And then in the middle of it, it can calm down before it has to build up momentum to jump again. So that's our idea. So in this Gibbs phenomenon, it's common at points of discontinuity, and the partial sums do not converge smoothly to the mean value. So these middle points, it's not going to converge smoothly to get to those values in there when we do partial sum. As you go up higher and higher and higher and higher to get your full summation, then it's going to smooth out a bit, but any partial sum is still going to give us trouble. Next up. So here's the idea that with our non-periodic is that we can non-periodic functions with series restrict the domain to desired period t. We extend the resulting function with the restricted domain so that f of x equals f of x plus t and is periodic to L. And so our goal with all of this, and let me separate that so you can see our distinct thoughts a little bit more clearly, is that we can write f of x in terms of only sine or only cosine, which will let us use only the b sub n's or only the a sub n's. So if we can, that would be nice. So try to get only things in the sine or the cosine. Makes life a whole lot easier. So if we are given x equals x for x in 0 to 1. So we want to extend this to make it periodic. Now we want to get it on both sides of the x-axis. So we're starting with this. So there are several ways we can do this, starting with this same basic beginning spot. So one thing we can do although we would have to make a minor modification to this, that one of these endpoints would have to be an open point. So make that an open point. So let's change this, get rid of that on the end. Let's make that parentheses. We could just repeat it. And in this case, and over here would also do it. It's an equal x plus 1 from -1 up to 0, and that should be not included. We'll see why that's not included in a second. it's going to equal just x when we're between 0 and 1. But now, at those discontinuity points, you would need to redefine there. So this one, x is going to equal 0, 1, 2, all those values that are in between where we have our discontinuities. And so there are a few ways you could rewrite this. One could potentially just be n, where n is an integer. So at 1, at 2, at 3, at 0, at -1. If you don't have to list all of them. Although for this one, we're only worried about between 0 and 1. So 0 is included, 1 is not. So we would do -1 and 0. Keeping in mind that f of x plus 2 can equal f of x. But since we are officially saying that in our original, that point is included, whenever we extend it, that point is included and this one's not. So that's why we're going to establish that. Other ways we could do this. Is we could just extend it that way. That would then be included there as well. So included, not included. Although whenever we make our change, then we would drop those points. And we put it right in the middle. What else could we do? We could do that. Now, for our first period, that one's not included. But then as we start filling in, or whatever we end with, that would have to be not included because we wanted to not have that final endpoint. And a third one, or sorry, fourth one, another one we could do is we could go up to 1 and then go over. So that would be included, not. Of course, for our points then, discontinuity. So that's filled in. If I can fill in the circle, open, fill that in, open, fill that in, open, whenever we make our change. So there's our Fourier convergence theorem and how we can model this and what the graphs would look like and how we extend this and apply the Fourier stuff to even non-periodic functions.